This playlist is about a topic that surprised me when I first found it out. It may surprise you as well. I shall show here how I thought wrongly about one of the most basic physics experiments possible. And judging by what I find in many common textbooks and websites, I am not the only one with these misconceptions. The experiment is this. We take a container of water and dip a pencil in it. Now, if the pencil is tilted, in that case you can see that there is a bending at the point where the pencil enters the water surface. Now, if you hold the pencil vertical, in that case there is no tilting. The pencil does appear straight. And even if you move the pencil closer or away from your eye, it still appears to remain straight. And when you do this, you have to carry out the entire experiment with only one eye, keeping one eye shut. Sounds familiar? I bet you have heard about this during your school days. This is one of the few experiments that most people actually perform on their own. And we all think that we know the explanation, right? It is caused by refraction. Let's make a little diagram. Here is the pencil. Now consider a ray coming out of the tip. It is refracted away from the normal as it emerges into air. Now, if we take another ray also from the same point, that also undergoes a similar refraction, but at a slightly different angle. These rays appear to have come from a different point, this point. So the eye thinks that the tip of the pencil is actually here. A similar thing happens for each of the points along the entire pencil underwater, so the pencil looks bent. But why should the pencil appear straight if it is kept vertical? Simple. Perpendicular rays do not deviate during refraction. That is why. But are these two simple explanations correct? No. Both are utterly wrong. Let's see why. Let's take the second explanation first. The case of the vertical pencil. True, the pencil now enters the water perpendicularly. But the rays that reach the eye do not leave the water perpendicularly. Since the ray hits the water surface obliquely, it is deviated. After all, the law of refraction is not for the pencil, but for the light rays. Now let us take another nearby ray. Unlike last time, here we have drawn them really accurately, taking the law of refraction into account. We have taken mu equal to 1.3, which is the correct value for water. This accurate diagram shows that the point of intersection is much nearer the eye. Indeed, if these rays make around 45-degree angle with the horizontal and the pencil is dipped about 10 centimeter below the water level, then this distance between the pencil and the image is about 7 centimeter. So the pencil should look extremely bent. Not only that, if you move your eye catching a different set of rays, then the point of intersection moves with it. This means the tip of the pencil should appear to move as you move your eye up and down. We have shown this path using this red line. Indeed, this book by Jenkins and White, Fundamentals of Optics, claims that this really happens in practice. They provide this diagram showing the red line in greater details. They claim that as the eye moves, the tip of the pencil indeed appears to follow that curve. But a simple experiment is enough to convince you that this is wrong. The pencil does not appear bent, and though the tip does appear to move with the eye, it moves only vertically and not much. Nothing like 7 cm for a tip only 10 cm down in water. Before we provide the correct explanation, let us show a couple of inadequate explanations found in some sources. This explanation takes the law of refraction and replaces these two signs by tens. With this modification, the pencil indeed remains straight, as you may convince yourself easily by doing the simple math. This modification is justified if we consider nearly vertical rays, like a man standing in a pool looking at his own feet. Here, both these angles, this R and this I, are close to 0, and so their cosines are nearly 1, hence sine and tan are indeed approximately equal. But the pencil experiment involves looking at angles far from the perpendicular, so this explanation does not work here. I have not seen this second explanation in any book. It was furnished by a friend. His contention is that since the pencil bends towards us and we look through one eye, we cannot feel the bending. It just seems that it has become shorter, what is called foreshortening. Like if I point my finger upwards, you see its full length. But when I turn it more towards you, its apparent length seems to decrease. It seems to have become shorter. True, but still you can easily understand that my finger is now pointing away from the vertical, and not that it has just magically gotten shorter, still pointing upwards, right? Even with a single eye, we can pick up enough visual cue to distinguish foreshortening from actual shortening. If you are not convinced, just do this experiment. Take a flat ruler and hold it under water really tilted towards you. Now, look at it with one eye. Does it appear to be a shorter vertical ruler? No. This is clearly different from this. Now it is really vertical. So there is no way you can mistake this for this. And this bending is far more extreme than that. So there is no way our eye could have missed that. Well, I hope that I have been able to convey the problem to you. Keep thinking about your own solutions. In the next video, we shall come up with our solution.